Did you do it?
Yes.
What did it cost?
Everything.
But it doesn't have to cost your agency. There are still some places where you have a choice. For example, take the scenario where x squared is significant, but x is not significant. Should you leave this variable in the model or not? And there's a debate. Some people will say you should leave it in. It's not really hurting things. And if you don't put it in, then you're going to restrict what kinds of quadratics you can have, because ax squared plus bx plus c describes any quadratic. But if you just have ax squared plus c, there's only certain quadratics you're allowing. And if x squared is needed, then it makes sense that x should be part of the model. Other people, though, would argue that you should take it out. That's our rule, right? If the p-value is not significant, then it's not helpful and it shouldn't be there. It'll also leave you with a model that's smaller, a little more simple. Which position is the right one? Actually, neither and both. Doing it either way, you will get a model that's pretty good at making predictions. Often this is between people who are more applied or more theoretical. I don't care which one you choose. It does make sense that you should have a philosophy, and that's just what you follow. And we could, of course, make this even more of a weird scenario by saying x to the fourth was significant, but the third, the squared, and the x were not. Still the same idea. One philosophy says include them all because x to the fourth was needed there, and the other philosophy would say if the p-values are not significant, then go ahead and remove those. Keep in mind that if x to the fourth is needed, you should test these. This debate only happens when we have p-values for these and we see that those p-values are not significant. And speaking of testing higher order polynomials, there's a thing called fishing, which is okay in this class, but it wouldn't normally be okay in higher level stat classes. What does it mean to fish? Well, let's assume, for example, that we're testing x and x squared and x cubed up to x to the fourth and fifth, and you can go even higher, and weird things, maybe the square root or the log or trig functions or some bizarre function involving x. Well, if you try enough stuff, eventually you'll start to find terms that are significant. It may not necessarily be real that those were significant terms because you make type 1 errors 5% of the time. That's why we use an alpha of 0.05. So eventually, as you test more and more things, you're starting to find patterns in the static. For example, let's say that I just put some random data on the board. Even if it's truly just random data, if you eventually look at it long enough, you'll start to see patterns that aren't actually there. It's just random luck. This is why sometimes people will say, if you torture the data long enough, it will scream anything you want. The idea being, if you start testing enough things, you'll find stuff that's significant and you're really just overfitting the model. So higher level stat classes will say this kind of fishing is not okay. This class though, because you're learning, because you're still trying to get a feel for how things work, it is okay to fish. You can try all sorts of different curves until you find one that you like or one that gives you good residuals, and that's okay, we're allowing that. And there are other people who will say fishing is allowed when predictions are the only thing they care about instead of a model. So this is a little bit controversial. That's our rule for this class. Saying that you can fish does not mean that you're allowed to do anything you want. You cannot use r squared to say you have a good model. If you find significant p-values and your r squared is 0.99999, which sounds impressive, that is not enough to say that you have found a good model. It has to be based off having good residuals and small p-values. Go look at the last video if you're not sure why that's important. One last example that helps illustrate the debate that can happen between whether making your model simpler or leaving terms that matters. This is Einstein's famous equation. This is the actual real equation. But this piece right here, this PC, is often very small, especially if we're talking realistic scenarios of normal, not close to light speeds. And so people often say we can just ignore this if we we do, the equation becomes so much simpler. E equals mc squared is all you have to know instead of this whole equation. Is that better? Is that good? Well, it depends. Some scenarios might want this. Some scenarios might want all the x's. And sometimes all you want is a simple equation because that's easier to give to a client. That's the debate that you have to do in this class. Which one do I want to do? Have all the variables because that makes sense. They should be there if the higher order is there. Or keep my model simpler. You pick.